So why do I have pictures of children's toys kind of on this slide to talk about how we describe enzymes? Well, they're going to be helpful for how we think about enzyme activity and using specific enzymes within a metabolic pathway to control what we call flux. Okay, flux being flow through the pathway. So this short video here is really going to be about how we describe enzyme activity and describe it as either being near or far equilibrium. So this is how we describe enzyme activity. Okay, so starting here first with near equilibrium. Okay, so the sort of toy analogy I want you to think about is I want you to think about a seesaw or a teeter-totter, whatever camp you came from. So seesaw. And as I sort of go through this description here, I'm going to highlight sort of the main pieces that you need to make sure that you understand and know about and the differences between near equilibrium and far equilibrium reactions or enzymes. We're going to get to this a lot more next semester when we study, all 10 steps of glycolysis, and then we understand which enzymes in that process are near versus far equilibrium. And why this is really important is this is how we identify control points. So this is identifying sort of the rate controlling enzymes for metabolic pathways. So that's why this is important, is if we're looking for places where there is metabolic control of a biochemical pathway, it's going to be enzymes that operate far equilibrium. So let's understand near equilibrium first and understand that these are going to be enzymes that we don't control. And as we go through this too, I use water flow as a lot of an analogy to explain how we think about a flow through metabolic pathways. We call that flux. So I want you to think about whether or not we have a spigot, if you will, whether we have the ability to turn an enzyme off. Okay, if we do, that means it is a control point. We have the ability to control the flow of water through that gate, if you will. If we don't, that means that enzyme doesn't have the ability to be turned on or off in that way. And so we really don't control flux through that enzyme in a way where we have control over it. It is really subject to the whim of whatever metabolite concentrations are. Okay, so that being said, let's sort of like delve into what it means then to be a near equilibrium enzyme. So if you are defined as near equilibrium, you're always on. So you are always on, you're always R state. Okay, and what this means is that this enzyme is pretty much always close to its set point. Close to its set point. Okay, and what that means from a thermodynamic standpoint is that it has a delta G that's close to 0. And so this is one of these pieces I want you to know. Near equilibrium enzymes have delta Gs that are close to 0. And what this means is that they are easily reversible by changing metabolite concentrations. So they are easily reversible by changing metabolite concentrations. Okay, remember, metabolites are really reactants or products. And so this is where my teeter-totter analogy comes in, right? Depending on whether we're reactant heavy or product heavy, things are going to slosh back and forth through that gate, through that open hose, if you will, in our pathway to allow this enzyme to just respond to whatever metabolite concentrations are. If you're product heavy, go ahead and make more reactants. If you're reactant heavy, go ahead and make more products. That pathway, that gate is always open, so you're constantly moving metabolites back and forth based on that enzyme sort of set point to sort of get to what it needs its reactant and product concentrations to be. Delta G's approaching 0. Now, the key piece for this is to remember that this is not a good control point. So not a good control point. Right? Thinking about our hose analogy, this is not going to be a good place to control water flow through our system because we don't have the ability to turn the flow of water off and on with a spigot. Okay, so these are sort of the hallmarks, if you will, of near equilibrium enzymes and points in metabolic pathways. Delta G for these enzymes are going to be close to zero, and as such, they are not good control points. Okay, let's talk now about what it means if you are one of those enzymes in a metabolic pathway that operates far equilibrium. And the toy analogy I want you to think about is a slingshot. And you'll see why in a minute, but you can imagine that a slingshot has the ability, when you're pulling it back, to build up a lot of potential energy so that when you are ready to let go of it, you have a lot of energy moving in the direction that you want. Okay, how this happens, and again, these are set up parallel here. So how this happens is we have enzymes that are far equilibrium that can be temporarily off. So temporarily off, okay? And that is because they can be put into the T state, and that's because we have a spigot. So we have a spigot, right? We have a faucet that we can turn on or off to sort of stop the flow of water through that point in our hose, okay? And while near equilibrium reactions are close to their set point, far equilibrium reactions are far from that set point. And the reason that they're able to be far from that set point is we have turned off the pathway at this point, and so we've allowed an accumulation of metabolites on one side of that pathway, okay? So we get far from our set point, so it is allowed to get far from its set point, okay? And as such, delta G for far equilibrium reactions are going to be much less than zero. Said another way, they are going to be large and negative, okay? And we can sort of think about this as a Q versus K comparison. Oh boy, all that Gen Chem stuff that Dr. Parenti brings back, right? Remember that Q represents where you are at, okay, where you are at, and K represents where you want to be. That's your set point. And the larger the difference is between where you're at and where you want to be, that has to do with the magnitude of your delta G. Okay, so far equilibrium reactions with a large negative delta G means where you're at is far away from where you want to be. So that's how we set up the system so that it's a control point. Okay, so far equilibrium reactions are good control points. So good control points. And it's because we have the ability with these enzymes to turn them off. So again, the hallmarks of far equilibrium reactions and enzymes is they have delta Gs that are large and negative. And as such, because we have that spigot, that faucet, we have the ability to turn them off. They are good control points. So again, having the ability to turn these off are what make them good control points. Near equilibrium reactions and enzymes do not have the ability to be regulated in the same way. Okay, we're going to expand a lot more on that next semester when we look at entire metabolic pathways and we understand which enzymes are far equilibrium, why they're control points, and then again, looking at them structurally, understand how they are control points. Just as like a tie-in here from something that we've already talked about, we talked about phosphorylase. Phosphorylase is a far equilibrium enzyme that operates in the metabolic breakdown of glycogen, right? That is the control point for glycogen metabolism, for the breakdown of glycogen. There's actually other steps we're going to learn about in the glycogen breakdown pathway. We just, in this learning unit, learned about the rate controlling enzyme. But think about what we learned about with this enzyme. This is an enzyme that, based on whether that serine is out and phosphorylated or in or buried in that N terminus, that serine 14, that determines whether that enzyme is on or off, we can toggle between R state and T state between that enzyme. So that's an example of one of the many far equilibrium enzymes that we are going to learn about next semester.